Okay, my friends, prepare to be stunned. This girl is a PhD. She's trying to understand light. Now, let me just start off with her presentation of how she got involved in this double slit experiment and realized it changed everything she ever thought about light, even though being a PhD and studying light for I don't know how long, but she was pretty confident in the double slit experiment until she did the single slit, or a single break slit, let's call it that, and I'll show you this. And we did a very similar thing, only using a Venturi, and that I've been showing for many years now. And anyway, you'll see this in a second. I thought this was stunning, and it's going to give everybody a new perspective on how to design what I'm showing. I didn't really do a good job of explaining the Venturi at all, to be perfectly honest with you. So this was a much better explanation of what's actually happening at the point of contact of light and something that obstructs it. And they don't understand that light spins like this. Everybody thinks light is a wave. It doesn't. It spins in a circle. This is what they're missing. And I can present 100% evidence to show this. But let's see what she says. And you'll see this is going to be a fabulous presentation. Not because of what I'm showing, but because of what she's showing. Okay, get ready for this. This is absolutely fabulous. Listen to what she has to say about light. And she's a PhD, studies light. Here she goes.
How beautiful is this? This is an experiment in quantum mechanics called the double slit experiment, but I really didn't expect to see this when I did it myself. And seeing this changed my mind on an important question in physics. What is light?
So before all that, here's a simple experiment that you can do. All you'll need is a laser pointer and a strand of hair. So if I just take this laser and I shine it at this whiteboard here, you can see that you just get a dot. But what do you reckon will happen if I put this hair in the way?
You might expect the dot to get split into two dots, or for there to be a dark line through the dot, or nothing at all to happen since the hair is so small. But let me show you what actually happens in the dark, because it looks really impressive.
Surprising, right? And it's nothing to do with the hair itself.
Okay, that's obviously not a double slit experiment. We have a hair splitting the light. So why are we seeing all those pulsations? Okay, now let's go on a little further with this.
You can do the exact same experiment with anything thin. This is a variation on the double slit experiment, which is an experiment that's so important you learn about it on pretty much day one of any Quantum 101 class. The normal way to do the experiment is to shine a light on two very narrow slits.
Okay, this is the difference that Rod Warren did when he first tried to do this. He had two pins together like this with a slit between the two. So instead of being blocked here, he had this blocked here and he had a slit here. And what it did was, basically it was just like this. It was two very fine finishing nails with this exact same laser, a pulsed construction laser, which shoots out waves, and this phone from back in 2012, which is the Samsung Galaxy S3. And apparently he got the new phone and he decided to play around to do the same thing. And what he came up with is absolutely astounding. And it changes physics in a most profound way. What was most important for me is it proved my dipole electron flood theory, and we can actually see these dipole electrons, which they call Dirac neutrinos. We're going to get into that very deeply, but so that you can start experimenting, let me show you what she shows, because I wasn't good about how I presented the experiment. Rodney Warren did basically all the experiments. I did some, not much. I have the same stuff he had, and I duplicated what he was doing, but it's a very time-consuming process, not something that you can do in a few minutes. So you're going to have to dedicate some time to this and play around with all of the variations and the distances here and there, you know, what you have here and how far away you are from the Venturi, and the different sizes. And Rodney was using, by the time we sort of get towards the end of things, he was down in the very fine sewing needles he was using as a slit. And he was getting some fabulous. It depends on how far and wide the slit is. And now we're also thinking about a torus slit, so that everything wraps around in a circle, so that when you come through, all the fields have to go through the center, from the top to the bottom and both sides. And it might make a big difference. Who knows? There's a little engineering to do here, but not much. We showed, well, here, hold on a second. Let me show you what we found with Rod's experiment. All right, I'm just going to point out a few quick things here. This is what's called a Dirac neutrino. It's the smallest particles that exist. They say this is supposedly 1,000,000 times smaller than an electron, or neutrinos, which is just not correct. But that's what they do claim. Now, what do I claim? Well, let's find out. I claim that this right here is a muon neutrino, and that is an electron neutrino. These are the particles that CERN sees, and Fermilab and all of them see, and claim they are the smallest particles that exist. And I say, yes, they are. And they make up light. All right, a white one and a black one, and a white one and a black one. Back to back, they're like two bar magnets, which makes them a stable unit. One of these alone is not stable. It wants to attach to something. He wants to find something to attach to become stable and to grow into a stable particle. When they're not stable, they are heat, and they are like in space. It's the saturation of the ether particles that are in space. This is all light, and sometimes it comes off in photons, sometimes it comes off in bigger chunks, sometimes it comes off in just the white or the black. They can separate, and we did separate them, and here is the separation. This is what they look like when light comes flying down as light. All right, we accelerated this light and literally pulled that particle away from the wave, which is just like a jet fighter breaking the speed of sound, and then it exploded here, and the black split from the white. All right, believe it or not, that is fission. When something breaks apart, it's fission, and when something comes back together, it's fusion. So that's fission, that's fusion, and in between is raw neutrino electrons. Raw neutrino electrons, and that is part of the Dirac. Now, I believe we can use that raw energy to actually create free electricity, and I'll go into this later, but all you're doing is separating the black away from the white, and all we want is the white, because that's the only thing that fills your batteries up, is this white side. You have to separate this from that in order to get electricity for your battery, and then this has to find its way back to the black, and that runs through your circuits and drives your motors and all that stuff, and to get back to the black. It's the only mission in life for this particle is to get reattached to a black. And that's why as soon as they come out of the Venturi, they find the black particles. All right, they separate here, and they say, whoa, 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 where'd you go? Come back to me. And they come back together here. But in between here, that's just raw energy. That is free electricity, my friends. And I see no reason we can't harvest it by just putting a harvester right there. Run it right down into our batteries, just like I'm showing here. Very, very simple. Could be something you could carry around in a shoebox. All right, so this is what we're trying to hope to get, is free energy using this and seeing the smallest particles that exist. And when you can create electron showers, this is exactly what this is. These are electron showers. You see it? Electron shower? Electron neutrinos turn into electron showers. Now, they can only do this like for a pulse, and then they have to wait another week to charge it up, that type of thing. We do this all day long. We just run this, and it never has to stop. That's just all that is this right here. It's exactly like this. All day long. You never have to stop it. And putting that right into a harvester, we just got free energy. As far as I'm concerned, I see no reason this should not work. But anyway, for you that want to get involved in doing experiments, let me show you how to do this, showing you. It's sort of a roundabout deal. Okay, you see that? That's a Dirac neutrino, black and white. And guess what? We also see these in our light. This is light, so this is the smallest particles that exist, and there's that Dirac neutrino. Two of them back to back make up a photon. A photon is basically, the physicists do not understand this because they don't understand dipole electron flood, which means all particles are made up of these two particles. There's nothing that isn't made of these two. There is absolutely nothing. Your eyeballs, your ears, your hair, food, everything is made of these two particles. Bacteria, everything is constructed of these two particles in mass. Now, this is what I consider to be a proton. This is what the physicists say is a proton, one big ball of tightness that you can smash it to bits by hitting them head on, but otherwise that's not going to fall apart. Well, that's just not true. That particle there is 1,823 of these little magnets. They're nothing more than these. These are nothing more than magnets. Back to back, it's two dipole magnets. And that's a little dipole magnet right there. It has a positive and a negative. When you put 1,823 of them together, they turn into a proton. This is a photon. A photon is two of these particles together, two of these little dipoles, two little bar magnets. All right, and that's because there's two of them, it's sort of stable and it has a huge field that surrounds it. I mean, absolutely enormous. And that is what creates a wave. As that moves, that field has to move in front of it. And that creates a wave, as I also show right here. The particle is in here somewhere. And there's the wave because that's the magnetic field that surrounds the particle. And every other thing in the universe, there's nothing that doesn't have a field. Every single particle there is. You spit. When you spit, it's got fields around it. Everything has a field because everything's made of the same particles, and they're all made with one side that has a big field. The other side is just a black ball. And they know that, and that's called a muon neutrino. And as a matter of fact, right here, this is from Fermilab. They say this never changes. That's exactly correct. It never changes its size or weight, and it's very massive. And this can get big and small. Here's the proof right here. See that little glowy edge around there? There it is right there. You see this one's big and this one's small? That one's concussing as it goes forward. That's why this will get bigger and this will get smaller, and then they'll flip. And that's what makes them spin. It's called the muon wobble. And we can obviously see that it accelerated. And we obviously see the black came away from the white. There's no question about this. This is just, it's undeniable. No way you can deny this. And we started with light, and we created the electron showers and the sterile muons. They say that if you can do this, everything has to change in physics, which it does have to change because it's just not right. Everything is made of these little dipoles, which are little tiny bar magnets. All right, check this out. I find this interesting. This is about the Dirac neutrinos, and they say they are new and simple models that can simultaneously accommodate the Dirac neutrino mass at one end of the loop and the dark matter without invoking any discrete symmetries. Now, this is all new. They're saying this is new and simple model, which is mine. Now, this came out the 9th of April 2019. I wrote a paper on the 1st of April 2019, and well, actually, this was earlier than that. This was March of 2019. This is April of 2019, but, you know, right in the same time frame. But I had the exact same story here about the Dirac and explaining what the Dirac neutrino is. And they still don't understand it. Let me show you what they do say about the Dirac. But this was when all of this stuff was starting to finally come to the forefront. I had been posting about this for years, and finally it got so overwhelming that they started to respond a little bit. And this is one of the responses. All right, check this out. This is from 2015, and I had been posting papers to Fermilab and CERN and all these people prior to this time. Now, and this was about the neutrinos, because I could see them. I knew what they were. And this is the neutrino is a particle ahead of its time. They're talking about in physics classes, students are told nothing travels faster than the speed of light. However, that statement might no longer be true because of the neutrinos, which I showed traveling faster than the speed of light. A particle may also be able to transcend dimensions that light cannot. The concept of neutrino is significant to our understanding of the universe because the neutrino can be used to determine how fast the universe is expanding, which nobody can determine it because light slows down in the fields of the universe. So it has no, that's all nonsense. But here's what the important part is, all right? Here's what they say, listen to this. Everyone has heard of electrons, protons, and neutrons. All right, they say electrons are a little tiny particle like this, which is 100% negative, and these are like protons and neutrons. One of them has no charge and one of them has a charge. That's the only difference, and they're only different by 1 electron's weight. All right, so they say this is one tiny little negative charge, and this is a huge positive charge, and this is a huge neutral charge, which I disagree with all that. I say all of those are made exclusively of these. So this is nothing more than one more than a proton. Okay, a proton is 1,823 of these particles. So it wants one more to become neutral. And then it becomes a neutron. But in reality, it's just nothing more than a big mass of these particles. They don't separate into balls. They do have a periodic stability zone, yes. 1825 or so is stable for what we call hydrogen. And then helium is another element that is stable when it gets to be about 7,300 in that area. And then they grow way up from there. But they are just masses of these particles. They're not balls like this, they're masses of these. So if there was 10 of those, it would just be 10 times bigger than this, but just still looking like a snowball. All right, that's what the new chemistry is and the new physics is dipole electron flood theory. But look what they say about this about this neutrino. What exactly is a neutrino? Well, nobody knows. Well, I do. I know, I'm bragging again, but I'm telling you, it's true. A neutrino is an exponentially small particle with no electric charge. Not true at all. To put the remarkably small size of a neutrino into perspective, consider neutrinos are thought to be 1,000,000 times smaller than electrons. The neutrinos are the electrons. They just really missed everything. Of course, this goes back to 2015, and they're starting to catch up a little bit. And this goes back, what's this now? All right, this is the neutrino this is 2012. This was when I was interacting with Fermilab about these neutrinos and about our light experiments, showing them we found these particles. And there's also another one that they did here from Fermilab about, well, hold on, I'll show it to you. All right, you see this now? These are the particles. There's no question whatsoever. These are the exact same particles. It has the fuzzy edge around it, just like he says. Never changes size. It's like a bowling ball. That's the muon. And that one gets big and small, which is the point particle, has no mass. That's what fills your batteries up. Now, this is from 2013. Now, remember, the phone Rod got, he started to experiment in 2012. I can't remember whether I went to Fermilab to talk to them about this or not. I mean, I didn't actually go there, but I contacted Don Lincoln, who is the guy right here. Don Lincoln, who wrote this article, and I said, we have found your particles. Here they are. And I sent him all the information and all of our experiment results and everything. And he told me I was a tinfoil hat guy. Don't ever contact us again. And that was like, I don't know how many years ago, but it was a long time ago. But here it is right here. The extended particles is fixed. It never changes, the black one, but it has a fuzzy edge, which is that glowy little red edge. Yes, absolutely. Point-like particles are mathematical abstractions, zero size. They think they have no mass whatsoever, and they just almost have no mass. I agree with that. But they have a huge field that surrounds them. And that field is what plows through, and the particle is back here, which is the black particle is the pusher. And I can show this in experiments as well. The black pushes the white. And the white is a field. So you have a field, which is the wave, and the black primarily is the particle. But it's the black and white together. It's just that the white creates the field, the black is the particle that pushes the white. I don't know if I showed you this or not, but this is the phone right here, this Galaxy, Samsung Galaxy S3. Back to 2012, Rod did some experiments with trying to do the double slit experiment like that girl did, and he found all this crazy result. And this was back in 2012, and as soon as I saw it, I knew exactly what he was showing, and it was light, and it was the particles of light, and it was actually fission and fusion. So I worked with Rod for many years. And finally, we sort of went our own ways, and I haven't had any correspondence with Rod for several years now. You know, you can only go so long with this, and then you just finally say, well, nobody's going to listen. Well, why keep talking? And I think that's what he did. He just said, forget about it. And I never forget about anything. So I'm never going to forget about it, because like I say, it's never not going to be true. It's true now, it's true then, and it's never not going to be true. So they can avoid it all they want and just keep walking around in circles. But this will eventually be proven to be exactly what I'm showing. Because I have the evidence. This is no joke. I have evidence all over, and this is what I'm hoping we can get. Put this stuff in a box like this and get free energy. Because here it is, there's electron showers, high energy showers. The muons stay this way. Exactly what I'm showing. The high energy goes here down into the batteries. Anyway, I have all my evidence to prove these are the particles, and here's the particles right here. These here are these right here. That's what they are. And the other part of again, Fermilab shows the exact same particles, this glowy edge around it, and these puffy particles have no weight whatsoever, basically. And I agree with that, because the white particles right here, this is what makes your battery work. Without that white particle in there, your battery's dead. You fill that battery up with white particles, guess what happens? It doesn't get any heavier to speak of. Almost no change in weight whatsoever. But all of a sudden, that battery's got enough to drive you another 100 miles. How did that happen? Where did the weight come from? This has no weight, but it has all the burn. And it has all the energy. And once you break them apart, it wants so desperately to get back to that black, it will go through motors, it'll go through lights, it'll go through heaters, it'll go through resistance, and it'll push its way until it gets back to the mass of blackness. And then it becomes united again, which is a strong nuclear force. Okay, this goes back to 2016, all right? And long before that, 50 years since I was in the Army, I had the theory that there had to be nothing but dipoles. But I could never prove it until I saw Rod's work. And I eventually wrote a bunch of papers. I have like 45 papers up on academia.edu. And I was originally going to call this nuclectron theory, which means nuclear electrons. Because the nucleus was always thought to be just nothing but positive. And electrons, though, have a positive and a negative. Those are the Diracs. So this was not representative. So I changed the name to dipole electron flood theory. Okay, so dipole electron flood theory. That means a positive and a negative is the electron. An electron is not just a negative, as I showed you, or I think I showed you. Anyway, this talks about all of the different factors to consider. Light has no mass, that's wrong. Light's a fixed speed, that's wrong. Neutrons are neutral, that's wrong. You know, neutrons are neutral, yes, but there's no such thing as a neutron. It's just a mass of particles that is even numbered and at a certain quantity. These are nothing more than quantities, and they are huge quantities. I'm talking thousands and thousands and thousands of particles, where we thought there was 2 and 1. No, there's 1,825 instead of 1 particle here. There's 7,000 something instead of 4, which helium is supposed to be 2 protons and 2 neutrons together. And the only reason they throw neutrons in, because they had no way to work with them, because the masses were changing so fast, they figured, well, there's only, we'll call everything a proton, 1, 2, 3, 4, 5 up the line, and everything else in there we'll just throw in as neutrons. I'm not kidding you, that's the way they did it. So anyway, I said, this has got to be looked into. This is all, it's all guesswork what they're doing now. And then I say the electrons are tiny, approximately 1,800 times smaller than the neutrons. And these electrons are the dipoles. Now that goes back to 2016. And again, I have papers, I have all my documentation showing what I did back in the early 70s, right after I got out of the Army. I just went deep into this, but nobody would listen, and so I went into electronics, into my own business, and walked away. I couldn't do anything. I couldn't show any proof. But now I have all the proof. It's right here. There it is right there. And it's exactly, watch, this is identical to Fermilab. If you tune the Venturi correctly, you can let a little bit of black through, but really excite the white. And then you can see the black actually pushing the white, which is what I just talked about a second ago. The black is a pusher. The white is just energy, very, very energetic. In this case, the laser came down, and this is so tightly tuned that it would only allow the white through. No black came through with this. 100% white. And that is what you want to put in your batteries. So if you could collect it right there, you're good to go. All of the energy to try to generate electricity is used to try to pull the black away from the white. Well, here it just separates naturally. And then the black is actually working for us because it's pulsing. It's slapping that white. Bam, 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 bam. And we can regulate it. We can go, or we can go boop, 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 whatever we want. Whatever we want. Simple as that. Boom, 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 or fast or slow. And this is all design stuff we have to do to figure out what's the best design of the Venturi. Would it be a round cone to force things in, or this was nothing more than just two little pins through the pins, and coming out the other side, it came out here all spraying like that. And that's because light spins, and this is not interference patterns because of flaps. This is a single slit, and these white do not want to be next to any other white ones. That's why they set up these lines in between the strips of the white, because they push this way and the other ones push this way. And you want to see an extreme example of that? I got them pushing from all 3 ways. Look at this. Here's the pulse laser coming through here. A pulse laser means you get pulse, 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 pulse. Okay, that's what a pulse means. What is the white particle? The white particle is here. So its next particle and the next pulse is between, and you get an interference pattern. All right, you always have a black in between. It's called an interference pattern. I'll accept that. You see here, we have blacks all the way down here because this one white does not want to be next to that one. That one doesn't want to be next to this one. This one. So they set up these interference patterns of just pushing each other away, and these are pushing each other away because they're the pulsations. All right, stop and give yourself a time to think about these things. To look at it, say, "Ooh, look at that! Wow, that's fabulous!" Woo, woo, woo. Well, there's a lot more to woo, woo, woo than just fabulous. I look for what can I prove with these fields and so forth, and there they are, right there. Here they are. I'm showing you everything that you need to see right now to prove that light is a particle, okay, which is this particle right here. All right, and it's a photon. And beyond that, half of that is an electron right here. That's a dipole electron. They call it Diracs, call it whatever you want. It's a dipole electron. We never knew the black was attached to the white. And here's the particle coming in slow in a neutrino phase where it's not quite a photon yet. And then it picks up into being a photon, and then it exploded at the Venturi. Precisely what I've shown hundreds of times for, it's got to be close to 10 years now. And this is all it is a dirac, exactly what they say, the black and white particle. And then when we get down to electron showers, which we absolutely did, that's electron showers. Here they are, electron showers. No question and this is not my writing up here. This is from CERN and Fermilab. All right, the muon stays the black ball. It never changes, and it never does. I agree with that. And we separated it from the electron neutrino, causing electron showers. Well, what do you get out of electron showers? Here's what you get out of electron showers. The energy of neutrinos, which is electron showers, a few 100 billion electron volts to trillions of electron volts from, let's say, a few million. That's a huge increase in energy. And that's the energy you need to just push that into your batteries, and you can drive all day long. And we can never stop producing this. We can just run this all day long into this a little handheld thing like this you carry around, you plug all your devices in. Simple as that. And here's the electron showers. They're low energy, and then they get to become really high energy. The muons back right off. See, these are the muons. They back right out. The electrons, this is from Lawrence Livermore. They agree. They agree with everything I'm saying. They just don't want to talk about it because it changes their status and their funding and their grant money. Because I'm telling you right now, this is just a big boondoggle at this point. And again, I presented this to Fermilab years and years ago. And I had never stopped going after them, and they just put you off in the woods. Don't talk to that guy. He's a tinfoil hat guy. Exactly what Don Lincoln told me. He says, you're a tinfoil hat guy. Don't ever contact me again. All right. I even took a course at University of Geneva just so that I could show them my research, which I did, and they sure seemed like they were impressed, but they didn't want to interact. They said they would follow me on Facebook. Now, you can go to from Coursera. You can go. I went to the University of Geneva free, online. You can join for free, and they don't give you any piece of paper that says you're smart. But I put everything in documents, and I save all the stuff that I did so that I have like a portfolio of my research work, and then of course I posted all kinds of things on academia.edu, and then I have some books and so forth. But I presented all this stuff, and nobody really was interested. They just wouldn't pay any attention. And what I have shown you, if you can miss what I'm showing you, I don't know how you can miss it. And if anybody wants to contest what I'm saying, I'd certainly like to hear why. So anyway, let's keep going. Okay, let's go back to Looking Glass Universe. And she did a really good job. I commend her for doing this. And I'm going to just play this again for a while here. It goes.
This is an experiment in quantum mechanics called the double slit experiment, but I really didn't expect to see this when I did it myself. And seeing this changed my mind on an important question in physics. What is light?
But before all that, here's a simple experiment that you can do. All you'll need is a laser pointer and a strand of hair.
So if I just take this laser and I shine it at this whiteboard here, you can see that you just get a dot. But what do you reckon will happen if I put this hair in the way? You might expect the dot to get split into two dots, or for there to be a dark line through the dot, or nothing at all to happen since the hair's so small. But let me show you what actually happens in the dark, because it looks really impressive.
Surprising, right? And it's nothing to do with the hair itself. You can do the exact same experiment with anything thin. This is a variation on the double slit experiment, which is an experiment that's so important you learn about it of pretty much day one of any Quantum 101 class. The normal way to do the experiment is to shine a light on two very narrow slits. Then the light that goes through the left or to the right.
This variation is pretty much the same. The light goes through one way or the other. But besides being easier to do this way, the other advantage is the pattern you get. You can see that they both have the same sort of flavor, but they're different. For example, the dashes of light for the hair version are all evenly spaced and get...
All right, let me just explain to you why that is. Because this light is coming down like this. It's not coming down like this and then they come through the other side and the waves flap back and forth like waves of water. No, absolutely not. It's coming through, and some go that way and some go this way. And because you have two slits, they're sort of broken up and they just get all blobbed together. Single slit, you get one going this way, you get one going that way. And the reason they come into these specific lines is because when these come through, they do not want to be next to that one. This one comes through, it says, you stay on that side. It says, all right, I'll stay over here, you stay over there. And they set up these lines. And they are repulsion lines because the magnet repels itself. So let's just go back to her again. Here it goes.
Get lighter as we go. But the dots of the double slit are much more patchy. That's because of something called single slit interference, which is basically a distraction in this scenario. So yeah, I kind of prefer the hair version. Plus, check this out. I'm using this smoke in a can stuff to see the actual beam, but look really closely at the beam, and you can actually see where the hair splits the light into two. How crazy is that? And looking at this, I think it's really hard to understand why you get the crazy double slit pattern when it seems like obviously you should just get a dot with a line through it.
So I've done my PhD in quantum stuff, and I thought I understood the theory of this experiment really well. And so my plan was just to explain it to you in a cute little video about how to do the experiment at home. Instead, I got sucked into an odyssey for the last few months where I did all kinds of variations on the experiment, and I ended up questioning pretty much everything I thought I knew about light.
Smart girl.
It turns out this experiment is just way more interesting than I thought. There's always been this debate in physics about whether light is made out of a stream of particles or light is some sort of excitation like a wave.
All right, I think I explained that pretty well. The particle is inside moving forward with a magnetic field around it, so it creates this wave around it. And again, I can show these. It's not something that I can't show.
The double slit experiment was meant to definitively prove that light is a wave, except later experiments seem to show that light has particle-like properties as well.
He got a Nobel Prize for that.
I used to hate this whole wave particle thing because light is clearly neither. A great analogy I heard for it is that light is like a platypus. It doesn't make sense to say that it's both a duck and a beaver at the same time because it is its own thing. But actually doing this experiment finally made me see the value in having good analogies to help you think about light. And in particular, it really sold me on thinking about light in terms of waves.
All right, it's not a wave like this. It is a spinning particle. Let me just verify these things so that we can get beyond thinking about it and try to understand what she's saying. All right, if this doesn't convince you, nothing can. This is red laser, pulsed red laser. This is the single slit here. This is what happens. Light spins down here. Now you see it's a bazillion different little spots here. So they end up making sort of a strong spot in the center on the back wall. But if you look carefully, you can see there's a million little swings. And this is nothing more than that swinging this way and some of them swinging over this way. But they're hitting all over the place here. Most of them end up coming through the center and they hate each other, so they get really glowy in the center. Out here, they're sort of working with each other. You stay there, I'll stay here. You stay there, I'll stay here. And that's what the interference patterns are. Now, it's strictly, 100% strictly, because it's a spinning particle. And this, if you go to a machinist, that right there is a drill bit. That is the face of a drill bit. It's screwing its way through the venturi. Now, this is what the red particles look like coming from this exact laser. They're all over the place. There's not just one little particle coming down here. There's a bazillion of them. And wherever they get close to each other in a bunch, in a bundle, they get glowy. They just hate each other's presence. Stay away from me, I'll stay away from you. And you get less glowy as you get further apart. You get real glowy when you get close. It's called the Kashmir effect. Now, obviously these are spinning little particles or pulsating little particles, but I can tell you absolutely for certain they are spinning. In the red, you're seeing them separated like this. In the blue, it's just so fast you can see them actually spin. You see these? These are spinning particles. And how do I know they're spinning? Because this one here is coming in real fast. and it's almost going straight, and then you see a curve way off this way. What it's doing is it's spinning in this direction. It's slowing down. You can see it's starting to spread out as it slows down. At the end, we can see there is two particles, which is all light photons have two whites and two blacks. And we can finally see them way out here. And now how can I say it's spinning? Because it's drifting to the left as it's spinning to the right. It's exactly what you would expect. It's coming here, and as this one picture takes it all at once, it's drifting to the left, the particle, because it's actually spinning to the right. It sounds counterintuitive, but just think it over. That's the only benefit I've ever gotten from the blue, is to be able to see it being very fast and then slowing down, seeing there is really two particles, and being able to be absolutely certain this thing is spinning. There's no question about it. So you say, well, Roger, maybe red is different than blue. Blue just does this, but red doesn't. But red is just a pulse. No, it isn't. Green is the same particle right here. There's green. It's identical to the red, only it's much faster and much more powerful. And the blue is the same. It has the two blacks and the two whites, but you never can see them. It's just too fast. Just too fast. You can't work with the blue. Green, you can't really work with either. But the red is really pretty simple to work with. And as that particle starts to accelerate and hit the Venturi, we actually see the particle changing from its neutrino into its photon, into its explosive state. And we could actually see that with the green as well. Here it is right here. You see, these are neutrinos. And that's a photon. The same particle, it's just much more powerful. It's coming from a much more excited push. And again, the black pushes the white. The black pushes the white. All right? And normally that would be a red, but once you start really pushing hard, everything turns white. Because that's luminosity. Luminosity is energy. What does that mean? That means we started here with almost no luminosity. Here we just got luminosity on steroids. That means we should have increased that energy value exponentially. And that means we should be able to get free energy with something just as simple as this. It's exactly what I showed you a second ago. Just like this. Carry it around, plug anything you want into it, any voltage, any cycles, any AC, DC, anything you want. And this is all because of electron flood theory. Without it, none of this would work. But with it, I think we can get free energy. And then we should be able to do this almost overnight. And they're all coming around to my theory now. You see this? Here, a strange landscape of particles inside a proton map like never before. They're all dipoles. They're all dipoles. They're saying inside of a proton, yes, they're all dipoles. They're all little magnets just like this. And they're finally taking account of it. But this will go on for 20 years before they ever come to any resolution where we should be able to do this in a matter of a couple of weeks. One way or the other, we would find out. Did we get an energy increase here? Or did we not? Simple as that. Come up with a little Venturi, come up with a photo receiver, and do some experiments in the lab. I can't do this. I don't have the resources to do it. And I don't have the inclination to do it anymore. I got to be honest with you. I'm fed up with the powers that be. In every single range of science. Science is not designed to advance. It's designed to stagnate and keep the people that are in power, their status, their grants, all of that stuff. It's just like Max Planck said, science advances one funeral at a time. Before we can get anywhere, that guy's got to get gone somehow. And this is exactly what I found. And in our government agencies, spending trillions of our dollars, literally trillions, and they're just walking around in circles and don't care about this, calling me a tinfoil hat guy, when I'm showing precisely what they're looking for. I'm not showing. Has anybody got any dispute with that? Anybody saying I'm wrong? If you think I'm wrong, speak up. I'd like to hear about it. And I want somebody that has some influence in the physics range in that realm. All these people that they're talking about, Arvin Ash and all these people, they're talking about physics, and they're getting millions of hits on YouTube, and they're really mouthing off, Sabine Hoffensfelder and all that. They're starting to speak about, this stuff we've been talking about probably isn't right. I've seen that recently. Almost all of them now are saying, I think we made mistakes. But that's as far as they go. I'm showing the mistakes they made. So let's get this fixed up and get some free energy. That's all I'm asking for. That's not a big ask, is it?